Okay, next one. Who's the last one in the previous session that read with us? I think it was Karim. Karim, was the last one that read with us, or Kumail? Mishal read. Yes,
It wasn't
Muhannad.
me.
It was Mishal. Muhannad. Read this one,
Yes,
Muhannad.
Mr.
I want you to read. Okay, let's finish it. This slide, read it, Muhannad.
Work and energy. On work, well, okay. Work and energy. Newton's laws and the equations of motion may be used to derive a relationship between work and energy. In the figure below, a box is pushed across an ice skating rink with a force F. Let's see how this force changes the box's energy.
So we will use Newton's laws and the equation of motion may be used. We will use both of them to drive an equation to calculate kinetic energy. Let's see. This will be in the next one. So if we know that, I will read this equation first. If we know that the acceleration equal force divided by m, this is Newton's second law. And this equation to find the final velocity, v final square equal v initial square plus 2ad, we can substitute 2ad equal, we can rearrange this equation to have 2ad equal v final square minus v initial square. So if multiply, replacing a with f over m, if we replace a in this equation by f over m, we can have this equation. I will take this and the other side and show it to you. And the board here. Control V. So we will rearrange the equation. So we have 2ad in one side and v final square minus v initial square. Nothing new till now. I will replace a with m over d. I will do this one in another equation here. I will replace a with m over d. Let me start with this one. We said that 2a, oh sorry. So we said that 2, I hate typing like this. Anybody know a solution for this typing, guys? Typing issue? Because I don't like typing on with mouse. طيب. Two.
I'm sorry, I have a suggestion.
Yes,
okay,
go
so
ahead.
there's something on in Jalil, I believe in books like in like electronic stores, they have something called this drawing pad thingy. It's like you plug it in your laptop, and then you draw with a pencil. I think it's not that expensive. It's like maybe 300 riyals to 500. It is kind of saying it's not that expensive. You get me, mister? And maybe it's gonna help you when it comes to writing, because you plug it in, and then you write on the pad.
I think the school provided to the teacher, so I will ask them for one. I think the school provided.
Cool. Because yeah, it's way better, and it's gonna be your handwriting is gonna be good. So yeah.
Yes, that's it. Thank you, Ahmed. V final square minus V initial square. Okay. So we will replace A by F over M from Newton's second law. So we will have 2F over M multiplied by D equal V final square minus V initial square. So F multiply D is equal to work. Let's circle it. F multiplied by D is equal to work. And To get rid of this 2 over m, I will multiply this equation by m I will multiply the equation by m, and I will, to get rid of 2, I will multiply it by half 2, which means half m. I will multiply all equation by half m. So this one will be cancelled. Half m will cancel 2 and we'll have m. And we'll have in this term half m the final square minus half m the initial square. I can take half m as a common factor, so work will equal to work done half m multiplied by delta v, which is v final minus v initial delta v square. Okay, guys, delta v square. And if you have constant velocity, then we could say that energy or kinetic energy is equal to half m v square. This relation, we call it work kinetic energy theory. Work equal to the change in the kinetic energy. This is kinetic energy. Okay, guys? So we can say that work equal final kinetic energy minus initial kinetic energy. Again, that one is final kinetic energy. We know kinetic energy equal half mv squared. And this one is equal to initial kinetic energy. So we could say that work equal Ke final minus Ke initial, or work equal to the change in the kinetic energy. So if we come back here, replacing A with this one, we have this one. So work will equal what? That's it. Work equal to final kinetic energy. Okay, guys, that's it. So let's go back to the equations here. I'll finish this one. So when you are applying force, this force is exerting work because you are moving a distance, this distance. And the velocity will increase from V initial to V final. So the work done is transferred into kinetic energy. The work done is transferred, to understand it better. Let me take this one with you, with me too. So let's explain what's happening here. So this is the force applied. The force applied causes this system to move a distance d, this distance d. In the beginning of the movement, was the initial velocity, and this is the final velocity. So the force have done some work. This work is transferred into kinetic energy stored in the what? In the system. And from here we come with a concept called conservation of energy. That work done by this woman is converted into kinetic energy. The system gain it. Work done by this woman, which is equal force multiplied distance. This is work done, transformed into kinetic energy gained by the system. And we can calculate this kinetic energy or gaining kinetic energy by the equation, by this equation. Work done equal the change of kinetic energy. Work done by the woman equal to the change of kinetic energy of the system. So the work is some kind of energy is transferred to kinetic energy by that the system will gain or will have it. And the work was done by the woman. They call it work kinetic energy theorem. That's what we call it. That's what they call it. Okay, this one. So let's come here. Muhammad. Muhammad Budi, did he read? Muhammad Budi is here, guys. I think that he's excused. He's not here. Muhammad, you read. Omar.
Okay.
Yes, your turn. Read this one.
Work and energy from the relationship weight equal half mass.
Work, not wait. Work.
Work, yes.
Yes.
Yes, work. We see that the work done on the box or any other object is related to the quantity. This one, the quantity, the kinetic energy is defined as the kinetic energy or K of an object of mass m and speed.
Yes. So the quantity half mass multiplied velocity square, we talked about it in the video too. This refers to kinetic energy or KE. So if any object is in motion, any system is in motion, so the kinetic energy will be calculated half mass multiplied velocity square. Okay. And we calculate it if the velocity is constant. If the velocity is changeable or is not constant, so you will take V instantaneous to calculate instantaneous kinetic energy. Okay, if you have a changing velocity. But if the velocity of the object is constant, so kinetic energy will be constant half mass velocity square, and the units of it is joule. And this joule equal to what? Kilogram. Half doesn't have any units. Mass measured in kilogram, and the velocity meter per second, and square it, so meter square divided by second square. So joule equal kilogram multiply meter square divided by second square. And previously we said that joule equal to Newton meter. So let's type this. Of course, this is important too. So from here we find the joule equal what? Kilogram times the meter per second square. And also we find previously that Newton meter force multiplied distance equal joule. So these are equivalent to joule. Newton times meter equivalent to joule, and times meter square second square equal to joule also. So let's come here. And let me pick someone else to read. Yahya?
Yes.
Read this one.
In general, the kinetic energy of an object is the energy due to its motion. Kinetic energy is measured with the joule, the same unit used to measure work. The following table provides some examples of typical kinetic energy.
Yes, there are jet aircraft at 500 miles per hour. Okay, this is 10 to the power 9 joule. And the car at 60 miles per hour, this is 10 to the power 6 joule, and so on. This is about 1 million joule. Okay, the kinetic energy of the car moving with 60 miles per hour. Home run baseball is 1000 joule. Person at walking speed, 50 joule. This is the kinetic energy. House fly in flight is 10 to the power -3, and so on. So these are typical amount of let's start from the beginning. Ahmed Al-Mulla, because I know it's Ahmed Al-Mulla. Ahmed, read this one.
Okay. The kinetic energy increases linearly with the mass and with the square of the velocity, as the following example indicates.
So, before we go to this example, I want to go to this one. I think let's take it. Yes, we take it. That's here. From this one, we find that kinetic energy is directly proportional with mass and inversely proportional with, and directly proportional with velocity square. Let's take this one and put it here. From the second row, the relation between both of them. Okay. So I will draw here two axes. vertical one, and horizontal one, vertical one, and horizontal one. If I draw the relation between kinetic energy and, I will draw here, this would be kinetic energy. Kinetic energy, and there is mass here. We will have a straight line. It will be a straight, the relationship will be a straight line as this one. So that is what? That's the relation between kinetic energy and mass. And the slope, again, we study the relation between kinetic energy and the mass if the velocity is constant. If the velocity is constant. And the slope in this case, if we take kinetic by mass, it will equal to half velocity square. The slope in this case equal to half velocity square. Slope from this relationship, divide, move mass to the other side, kinetic energy divided by mass will equal to half velocity square. So slope equal to half velocity.
Does the slope have to be constant or full?
Yes, if you study the relation, the slope will be constant because.
And the slope is always in a straight line, صح?
Say it again. Talk again, Faisal. I didn't hear you.
So the slope is going to be always in a straight line, صح? As the mass increases, the kinetic energy increases.
Yes, we study the relation between the kinetic energy and the mass, and they are directly proportional, as you see from this relationship. So it will be straight line. By increasing mass, kinetic energy increasing, and keeping the velocity constant. The slope in this case will equal to what? Half. You find the slope from here. Kinetic energy divided by mass, move mass to the other side here. You will find it equal to what? Half v square. So that's the slope for this one. Here I'm going to draw the kinetic energy. And here I will draw, not mass, I will draw v square. To find the slope, I'll divide the slope equal what? The y-axis divide the difference in y-axis divided by the difference in x-axis. The relation first between them is also straight line. And to find the slope in this case, you have to move velocity to the other side. I'm going to divide ke by velocity squared. So I move velocity to this side. What's left here is half mass. So slope equal half mass in this one. Again, to find the slope, you go to the original formula to divide the y-axis by the x-axis. Ke by velocity squared. Ke divided by velocity squared. The other side will have half mass, so the slope will equal to half mass. And the same thing applies here. If I want to find the Ke divided by mass, Ke divided by mass, the slope will equal to half v squared. So from this we can know that kinetic energy is directly proportional to mass and directly proportional to what? To velocity squared. What if I draw the relation between kinetic energy and the velocity, not square, but velocity only? Anyone can predict what would be the relationship? بعمل ازاي? You take it in math, huh? Take that in math, guys. If I'm going to draw the relation between only velocity, only kinetic energy here, and not velocity, but velocity square, not velocity square, but only velocity. The relation between them will be a, I don't know if they call it parabola or whatever they call it, but it would be a function of the second power, like this, something like this. You take something like this in math? When I said y equal x square.
Yes.
Something like this. Okay, guys? So that would be the relationship. That would be the relationship
I
between.
kind of forgot the problem, Mister. Can you re-explain it?
If I draw only velocity here, okay, and want to find the relation between kinetic energy and velocity, we'll have a relation line like this, not straight line. That I want to say it right now, okay? Matt, you can study it with the Mr.
Mister, why is it not straight line?
Hey, why is
Don't
it curved?
understand.
Because it will be only straight line in velocity square, not velocity. Like this. Directly proportional with
So,
velocity
Mister,
square.
if it is squared, it goes straight. If it's this, it
Yes.
goes curved.
Yes, that's it.
Okay.
Okay. Because kinetic energy is directly proportional with the square of the velocity. This means if the velocity doubled, the kinetic energy will increase 4 times, not doubled. If the velocity is tripled, this will increase 9 times, which is 3 squared. If the velocity increases 4 times,
Mister, I still don't understand why the graph looks like sometimes it's straight line and sometimes it's curved. I don't understand.
no, not sometimes. Here it's squared, here it's not squared.
But what's the difference? Why does this one become curved and the other one isn't?
Okay. Listen to me. This is something related to mathematics, not physics. When you have the relation between this variable square, directly proportional to this one you can release it and put instead of it, you may any other function, maybe beta or b. Okay, this is another variable. So kinetic energy is directly proportional with b, which is equal to v square. So you have 2 variables here, v square and kinetic energy. But if I have velocity, only velocity, not squared here, the relation between them, you can do it, Kumail, in a table. Okay, I will show you a table like this and try to draw it with your own self so you'll find it. You will do a table like this and you'll put here kinetic energy. Okay, and here velocity and here velocity squared. Okay. And we'll take some examples. 0, 0, 0. In the first, the velocity is 0. Second one, the velocity is 1, velocity square is 1, and this one was, for example, let's say 5. Okay. Let's have mass multiply this. It says that you have it 5. Then the velocity is 2. This one is 4. Okay, this one will be increased 4 times, so it will be 20. Okay, so the velocity becomes 3, velocity square becomes 9.
Okay, I understand now, Mister.
Yes, that's it. So that's one increase, 9 multiply 5, it will be 45. So draw something like this, you will find what I mean. So we'll find it's a relationship between kinetic energy and the velocity square, not only velocity. If you draw this one, you will find something like this. I'm not sure about this shape, but you will have a curved line. Okay, let's go back to this one. And we have taken this. Oh, we didn't finish this one. We have a problem here. Who was the next one to read, guys? Question is this to read? No. That's it. I think Ahmed Al-Mulla read again and Ahmed Tawfiq Mishal. عبد الله الملحم طبعا مش معانا.
Okay, Mr.
Read this.
Mr. Do you hear me?
Yes, I hear you. I want you to read this example. Read this example, 6.5.
The example.
Yes, read
A 3,900 kilogram truck is moving at 6 meters per second. What is the kinetic energy? What is the truck kinetic energy if its speed is doubled to 12 meters per second?
Yes. So it's written here, the mass is equal to 390 kilogram and the velocity is 6 meter. So kinetic energy half mass velocity square. Kinetic energy equal half multiply mass multiply velocity square, half multiply 3,900 multiply 6 squared. This is the kinetic energy if the velocity is 6. If we double velocity, the kinetic energy will increase 4 times. So I will multiply this number by 4 times because the velocity is doubled. If the velocity is doubled, this means kinetic energy velocity doubled. You double the 2, it means multiplied by 2, which is equal to 4. So the kinetic energy increases 4 times. If we double velocity, kinetic energy increases 4 times because it's a directly proportional with v squared, not only v. So that would be the answer. 4 multiplied 70 equal to 180,000 joules. Let me give you a quick quiz and a small one. I'll try to pick a small one. Okay, guys, just give me a second. Yes. Now I'll send you the link. Copy link, and the link is here. Okay, this is disappearing naturally. And that's the code for those who want to have the code. So join this course, guys. It's about work and energy. We have 12 students. I want 1 participant here. I will start, and I'm waiting for the rest of you to join.